This is Math 251, and we're in section 14.6. We're now going to begin to talk about a different type of integral called a surface integral. Just sort of fair warning, this section has surface integrals in both explicitly and implicitly defined functions. We're only going to concentrate on the explicit ones. So if you do read the section in your book, there's more information in there than what we'll actually cover. All right, so just to kind of set the stage, we've been talking about integrating a function over a curve, right? We started with our scalar line integrals, right? A scalar function, integrated ds over a little piece of arc length along a curve C. And then we went to vector line integrals. This is the vector, in this particular case, circulation integral. Again, over a little piece of arc length along the path C. And I probably should have also said this one. We also did f dot n ds. Also a vector line integral. Again, f dot n over a little piece of arc length S along a curved path C. What we're going to do in this section is say, what if, instead of integrating over a curved path, we actually want to integrate over a piece of a surface? Now, a curved path we can do with a single line integral, but a surface is definitely at least two-dimensional, probably even three-dimensional. So hopefully it makes sense that we're going to need a double integral in order to do this. We'll start by talking about the surface integral of a scalar function, and then in the second half of this section, we'll talk about the surface integral of a vector function. So a scalar function, f of x and y, can be integrated over a surface S, defined by the equation z is equal to some function of x and y, this way. The double integral over the surface S of f of x and y, d capital S, notice this is now a little piece of surface area, is equal to the double integral of the f of x and y times this little radical, this correction factor here, square root of z sub x squared plus z sub y squared plus 1 dA. Notice that what's happening here is the ds is being replaced by the square root of z sub x squared plus z sub y squared plus 1 dA. What you're actually seeing here, and this may look familiar to you, is this is actually the formula, the integration formula for arc length. And if you imagine taking a little piece of arc length and pulling it through an area, you're going to create a curved surface, right? An arc pulled through an area. So that's where that d capital S comes from. So that piece of surface area we calculate this way. dA is integrated over the region R being the projection of S down into the xy plane. Okay. This is written for surfaces that are defined as z as a function of x and y, but I'll leave it to you. You can imagine exactly how they would look, I'm sure, if they were defined either of the other two ways, x a function of y and z, or y a function of x and z. For our purposes, we're going to stick with the z as a function of x and y, but again, nothing really changes other than the variables to do the others. All right, so let's go ahead and try one of these. I'd like to find the double integral over the surface S of e to the x squared plus y squared, ds, which is what tells me it is a surface integral. And S is the surface of this paraboloid for z between 0 and 8. So just to get a feel for what we're doing here, let's imagine what that looks like. That's just a paraboloid at the origin with its vertex, like so. And we stop when we get to a height of 8. Or it was supposed to be an 8. I didn't write that very well. 8. So it's this curved surface. It's like kind of a steep bowl, if you will. We're integrating this function over that surface. All right, couple of things. First of all, let's think about if this is S. Looks like polar coordinates is probably a good idea here, so I'm going to go with 2r squared for that equation. And the region R would be the projection of this surface down into the xy plane. If I imagine intersecting the z equals 8 with the z equals 2r squared, I get r squared is 4, or r equals 2. So if I were to imagine projecting this down into the xy plane, I would see a circle of radius 2. Oops, you couldn't see that, sorry. Move that down, there we go. All right, the next thing I'm going to need is I'm going to need that square root of z sub x squared plus z sub y squared plus 1. So let's think about that for a moment. Let's see here. The derivative of z with respect to x would be 4x. I have to square that. And then z with respect to y would be 4y. And I have to square that. And then there's a plus 1. So that's going to be a 16x squared plus 16y squared. Since I'm going polar, I'll call that 16r squared plus 1. I think I pretty much have everything I need. I'm going to scoot this down a little bit again so we can see the equation. To do my integral then, I'm going to take the double integral over my region R. R was that circle of radius 2, which is cut off a little bit down here, but I can redraw it. There. So R goes from 0 to 2, and theta goes from 0 to 2 pi. Of my function itself, my function in polar will be e to the r squared. And then the ds, I have to plug in as this radical, which we've already kind of pre-calculated as the square root of 16r squared plus 1. dA, so since we're in polar, that's going to be r dr d theta. Okay, so hopefully all the pieces are there. The function itself, the ds, where we had to put this radical in, and then the dA, r dr d theta. All right, this one's kind of nice. There are no thetas anywhere except for in the d theta, so I can just go ahead and pull that 2 pi down. Put my r out in front here. And I'm going to be really happy that I can do this on the calculator. That would not be a fun integral to try by hand. Let's see, I did do that, and I didn't get anything particularly nice. The integral itself gave me 187.513. And when I multiplied by 2 pi, I ended up with 1,178.177. All right, so let's talk a little bit about what we just calculated. What is that? What does that 1178 mean? Well, in fact, what we did here was we calculated an integral of some quantity over a surface. If you imagine this quantity that we integrated as a density function, the density of the material that's used to create that surface, then you could imagine that what we just calculated was actually a mass. It would be the mass of that bowl, given that that's its density. It gets more dense the further away from the origin we go. So that's one interpretation of that surface integral. In fact, if you look at the next page, that's one of the applications listed here. If I integrate a density function, then I'm going to get mass. If I do the surface integral of just the function 1, I'm going to get surface area. right? Remember, if you integrate 1 dA, you get area. If you integrate 1 dV, you get volume. If I integrate 1 ds, I'm going to get surface area. All right, so speaking of surface area, let's go ahead and find a surface area. I want the surface area of the portion of the plane, z equals 8 minus x minus 2y, in the first octant. So what does that look like? First of all, that plane, if I rewrite it, would be x plus 2y plus z equals 8. So thinking about the intercepts, x-intercept would be 8. Y-intercept would be 4. And z-intercept would be 8. So within the first octant, I'm going to see that triangular surface. And I want to find the surface area of that triangle. All right. In order to do that, I'm going to do a surface integral. And let's see here. We want to start by saying, what does R look like? So let's do that. I'm just going to scoot this up so you can see what I'm doing. R, remember, is the shadow or the projection down into the xy plane. So R would be this triangle, the shadow of the plane in the xy plane. And the x-intercept was 8. The y-intercept was 4. So this is my region R. All right. I do need that square root of z sub x squared plus z sub y squared plus 1 to go into my integral. And I've got the equation for z right up here. So with respect to x, that would be negative 1, square that. With respect to y, it would be negative 2, square that. And then the plus 1. Gives me 4, 5, 6, square root of 6 this time, just a nice constant. And so I'm going to say my surface area, which is the surface integral of 1 ds, can be written as the double integral of the function 1 times the radical, square root 6, dA, and I'm going to go with a dy dx this time for my dA. Let's see, if I think vertical rectangles here, that line would be y equals negative 4/8, so negative 1/2 x plus 4. So the y's go from 0 to negative 1/2 x plus 4, and the x's go from 0 to 8. I'm going to pull the square root of 6 out. And then I'm just going to integrate 1 dy, so that would just be y. And plugging that in, I'm going to get negative 1/2 x plus 4 minus 0 dx. And just doing that integral either by hand or calculator, it's not a very challenging one. I think that gives us 16, so we're going to get 16 times the square root of 6 for the surface area of that piece of the plane, that triangular piece in the first octant. All right, so those are the scalar surface integrals. We will pick this up and do a part B, and we'll do the vector surface integrals in that part.